Hello everyone, welcome to the second lecture of differential equations. Before starting the lecture, I want to tell you something that my video capturing device, that is laptop's camera, is not working right now, and I have been facing this problem since 2 days. And another thing is, I saw in the comment section that you guys are preparing IIT JAM syllabus. Let me tell you that the way I am teaching and the courses I am going to cover, it is JAM syllabus only. If you see the syllabus of JAM and CSR net, then there is no difference, because if you in the JAM syllabus, if you add a Green's function and the numerical methods, then this becomes net syllabus. So the questions I am giving you as homework, or I am discussing in the class, that are very important. Basically, I will be discussing very simplest example and give you some homework that are of a kind of advanced type. So you have to do those problems and analyze those problems. And the question I asked you to do last time, it was, just see the problem. It was saying that there is a mass here, m, it is moving with velocity v, let's say, and it is along positive x direction, and a resistive force minus gamma v square is acting on it. So in the questions, it did not give the differential equation. First you have to establish the differential equation. After that you have to solve that equation. I think this is clear. Now let's establish the differential equation. We know from Newton's laws of motion that F is equal to ma, and here F is only minus gamma v square. So by putting minus gamma v square, this becomes ma. So here this term is in velocity. We have to write this RHS in terms of velocity as well. So we know minus gamma v square is equal to ma. We can write acceleration as dv by dt. Then we can clearly see that it is a separation of variable type of differential equation, and by separating the variables we get dv by v square is equal to minus gamma by m dt. Now you can integrate both sides with an arbitrary constant c, and its integration will be minus 1 by v is equal to minus gamma by m t plus c. Now we have been given an initial condition, that is v at time t is equal to 0 is equal to v naught. Let's apply this boundary condition to this equation, and it becomes minus 1 by v naught is equal to 0 plus c. So the value of c becomes minus 1 by v naught. Now put this arbitrary constant in the equation, and the equation becomes minus 1 by v is equal to minus gamma by mt minus 1 by v naught. And after arranging this equation, we will get the answer v is equal to m v naught divided by m naught plus gamma v naught t. So here we saw that differential equation was not given. So first we have to establish. Now they are asking this kind of questions, in which you have to first establish the differential equation, then find the solution of the differential equation. Then in some cases it is giving to analyze the solution. I am giving you another problem in which you have to analyze the solution as well. Okay, so let me go to the next slide. Okay, so I'm giving you another homework. This is also very important, because the questions I am giving you as homework that are from CSR net exams. And so try to solve, at least try to solve. If you cannot solve, I will solve in the class, so don't worry about that. Okay. So let's take the question. Let's say you are given a differential equation dy by dx as y square by x with the boundary condition y at x is equal to 1 is 1. Now he is asking to find the range of x in which y is real and finite. So the options are minus infinite, less than is equal to x, less than is equal to minus 3. Second option is minus 3 less than is equal to x, less than is equal to 0. Third option is 0 less than equal to x, less than is equal to 3. And last option is 3 less than is equal to x, less than is equal to infinite. Let me give you a hint here. First, try to solve this differential equation, solve the differential equation. Then this will give you the relation between y and x. Y is a function of x you will get. Then see for which x value you will get this y is real and finite. So this value of y will not be infinite and it will not be complex number. So try to find that. Let me go to the next slide and let's discuss the second type of ordinary differential equation, that are the equations which can be reduced to separable ordinary differential equation. So here in this case we make some suitable substitutions, and after this substitution is made, the given differential equation becomes a separable type of ordinary differential equation. Now let me take an example here. Let's say we are given the differential equation as x plus y plus 1 whole square dy by dx is equal to 1, and we have been given the initial condition x at 0 is y at x is equal to 0 is minus 1. So here we have to make the substitution here. So let's take this x plus y plus 1 is equal to v. After differentiating both sides with respect to x, you will get dv by dx is equal to 1 plus dy by dx. Now we can write down dy by dx as dv by dx minus 1. Now substitute all these things in this equation. We will get v square dv by dx minus 1 is equal to 1. Now we can rearrange this. This becomes dv by dx. We can take v square here, it will be 1 by v square, and minus 1 becomes a plus 1 in this side. So we can write down 1 plus 1 by v square. Now again we can write down dv by dx is equal to 1 plus v square divided by v square. Now we can separate the variables by taking all these terms to this side and this dx to this side. It will be v square dv by v square plus 1 is equal to dx. We can take integral on both sides with an arbitrary constant, and here we can add plus 1 and subtract 1. It will be v square plus 1 minus 1 divided by v square plus 1 dv is equal to dx plus c. And you know this by dividing you will get this term becomes 1 here, and it will be minus 1 by v square plus 1. Now we get 1 minus 1 by v square plus 1 dv and its integral is equal to x plus c. You know the integration of 1 is v, as it is being done with respect to v, and this gives us tan inverse b. So we will get v minus tan inverse v is equal to x plus c, and we know the value of v here. This is x plus y plus 1 minus tan inverse x plus y plus 1 is equal to x plus c. Now we have been given this condition here, y at x is equal to 0 is minus 1. So now let's put all these things. Then this equation becomes x is 0, this is minus 1, this is plus 1, minus tan inverse 0 minus 1 plus 1 is equal to 0 plus c. Now all these things gets cancelled out, and this becomes tan inverse 0. So you know the value of tan inverse 0 is, it becomes 0. Then this equation becomes x plus y plus 1 minus tan inverse x plus y plus 1 is equal to x. Here you can cancel x, so this side will be 0 and it will be y plus 1. I think this part is clear. Let me go to the next slide, and this is type 3 of ordinary differential equation, that is homogeneous ordinary differential equation. Let's see what is the definition of a homogeneous ordinary differential equation. Let's say we have a function f of xy. It is called homogeneous only if here we will put x, lambda x in place of x and lambda y in place of y. Now if function of lambda x lambda y becomes lambda power n function of xy, then this is called homogeneous ordinary differential equation. Now this n is called the order of that differential equation, or if we have a function, then order of function. Let's say let's take an example. Let's say we have a function as x to the power 5 plus 3 square y cube divided by 2x square plus 5xy. First we have to substitute lambda x in place of x and lambda y in place of y. So this equation becomes f of lambda x lambda y is equal to lambda power 5 x to the power 5 plus 3x square lambda square and y cube lambda cube divided by 2 lambda square x square plus 5 lambda x into lambda y. So from numerator we can take lambda to the power 5 common, and from denominator lambda square is taken common. By cancelling we will get lambda cube f of xy. So this is a homogeneous function with order 3. Now what we have to do if there is this kind of differential equation, let's see some points. Here we have to substitute y is equal to vx or x is equal to vy. In which case we have to use this, and in which case we have to use this. Let's see that. Whenever there is terms like x by y whole power n, cos x by y, or e to the power x by y, or tan inverse x by y, in that case we will use x is equal to vy. And whenever there are y by x whole power n, cos y by x, e to the power y by x, or tan inverse y by x, in these cases we will apply y is equal to vx. Now let's summarize this slide. So a function f of xy will be homogeneous if we substitute lambda x in place of x and lambda y in place of y, then we will get function of lambda x and lambda y is lambda to the power n into f of xy. Then this kind of differential equations or functions will be called as homogeneous function or a differential equation. Now we saw an example here, and for these homogeneous ordinary differential equations, what we have to do is we have to substitute y is equal to vx or x is equal to vy, and whenever there is x by y terms, in those cases we will apply x is equal to vy, and whenever there is y by x terms, in those cases we will use y is equal to vx. Now let's go to the next slide and see an example here. Let's say we have an differential equation as dy by dx is equal to y by x plus sine y by x, and I told you that whenever there is y by x terms, in those cases we will substitute y is equal to vx. Then by differentiating we will get dy by dx is equal to, first we will differentiate with respect to x, this x term becomes 1, we will get v, and by keeping x constant we will find dv by dx. Then we can write down dv by dx as okay, we will not do that, we will directly substitute this value here. Now we can write down dy by dx as v plus x dv by dx is equal to, we have substituted y as vx, so this will be v, and here it will be sine v, so we can cancel v on both sides, then this will be x dv by dx is equal to sine v. Now we can do the separation of variables. This becomes dv by sine v is equal to dx by x. Now we can integrate both sides with an arbitrary constant c. We know the differentiation of 1 by sine v with respect to v will be I think it will be log tan v by 2. Just check it, I think this is correct, and on this side it will be log x plus this arbitrary constant becomes log c. Remember, whenever we are not sure about this integration, so I have used c here, but after the integration, whenever you get log terms on either sides or on one side, then we have to take this arbitrary constant as log c. Now we can write down, we know the properties of logarithm, so it will be tan v by 2 is equal to cx, and I forgot to write here, this condition is y at x is equal to 2 is pi. We know the value of v, this is y by x, so by substituting you will get tan y by 2x is equal to cx. Now put this initial condition, so here we get tan y at 2 is x is equal to 2 is pi, so here pi by 4 is equal to c into this becomes 2c, then this is 1, you know, then c becomes 1 by 2. Now putting this value of arbitrary constant, you will get tan y by 2x is equal to x by 2. Now this is the answer. Okay, I think you got the whole thing. Whenever there is y by x term, and then you will put y is equal to vx, and whenever there is x by y term, you will put x is equal to vy. Okay, so now let me go to the next slide, and you will see we'll see the type 4 of this ordinary differential equation. This is linear ordinary differential equation. I have already explained you about the linearity of the differential equations when we are going to call it as a linear ordinary differential equation. Now let's take the general formalism here. So the general formalism goes as we will be this differential equation in the form of dy by dx plus p of x into y is equal to q of x. Here you can see y has power is equal to 1 and dy by dx has power is equal to 1, and there is no y into dy by dx or dy by dx into d square y by dx square terms, like these terms are not here. So we can say this is a linear ordinary differential equation. Now what we have to do is we have to find the integrating factor in this kind of differential equations, and this integrating factor is given by e to the power integral of p of x with respect to x. This will give you the integrating factor. After finding this integrating factor, we can write down the solution of this kind of differential equation as y into this integrating factor is equal to q of x into integrating factor. We will take the integral of this term with respect to dx with respect to x with an arbitrary constant c. So this is the solution of this kind of ordinary differential equations. Now let me take an example here. Let's say we are given a differential equation as x plus y dy by dx minus y is equal to e to the power 3x x plus 1 whole square, and this initial condition is y at x is equal to 0 is equal to 1. Now let's explain this problem here. Answer. So how we are going to do it? You see, here we have there is x plus 1 term, but we have to do this coefficient 1 first. So now let's divide x plus 1 in all the terms. Then this equation becomes dy by dx minus y by x plus 1 is equal to e to the power 3x, and after dividing x plus 1, only one x plus 1 will remain here. Now we got the same form as discussed here. Now we know that px is minus 1 by x plus 1. So we can find out the integrating factor here. It will be e to the power integral of minus 1 by x plus 1 dx. And this is, you know, integration of 1 by x plus 1 will be log x plus 1, and here is minus sign log x plus 1. And you know the property of this logarithmic and exponential, and then this will give us e to the power log x plus 1 whole power minus 1, and this gives us x plus 1 whole power minus 1, and this is 1 by x plus 1. So we can write down the solution of this differential equation as y into 1 by x plus 1 is equal to e to the power 3x x plus 1 into 1 by x plus 1. So here this part gets cancelled out, so this becomes 3x. We have to take this integral dx plus c, and integral of e to the power 3x is e to the power 3x by 3. Now this is the solution we got. Now we have been given a condition, boundary condition. Let's apply this in this slide. So the solution we got is y by x plus 1 is equal to e to the power 3x divided by 3 plus c, and the initial condition is y at x is equal to 0 is 1. Now put this initial condition, so this becomes 1 by 0 plus 1 is equal to 1 by 3 plus c. Then we get the c value 1 minus 1 by 3, that is 2 by 3. Now put this arbitrary constant value in the solution. Y by x plus 1 is equal to e to the power 3x by 3 plus 2 by 3. Now this is the solution of the given linear ordinary differential equation. So basically what we did, whenever there is the linear ordinary differential equation, this should satisfy. Let me just change the color of the pen here. Yeah, so the general form of the linear ordinary differential equation is this one. If in doubt, just check the linearity conditions, that is the power of y must be 1 and the power of all the derivatives of this dependent variable must be 1, and there should be no terms like y into dy by dx or y into d square y by dx square or dy by dx into d square y by dx square. Then if these conditions are satisfied, then we tell this equation is linear ordinary differential equation. Now in this case, what we have to do is we have to find out an integrating factor which is given by e to the power integral of px dx. After finding the integrating factor, we can directly write down the solutions as y into integrating factor is equal to integral of q of x into integrating factor with respect to x plus an arbitrary constant. And if we are given any boundary conditions or initial conditions, we can find out the value of c. After putting the value of c, we will get the solution. We saw an example here. I think this part is also clear to you. Now let me go to the next type of ordinary differential equations. The next type is Bernoulli's equations. So basically these are the equations which can be reduced to linear ordinary differential equation. These Bernoulli's equations can be reduced to linear ordinary differential equations, and how this can be done, let's see that. So the general form of these Bernoulli's equations are these are written as dy by dx is plus p of x, this is p, into y is equal to q of x. This is multiplied with some power of y. What we have to do here is we have to take this y to the power n to this side, then this will become 1 by y to the power n dy by dx plus p of x by y to the power here we get n minus 1 is equal to q of x. Now let's take this 1 by y to the power n minus 1 as v here, then differentiating with respect to x on both sides, we will get 1 minus n into y to the power minus n dy by dx is equal to dv by dx. Then then it can be written as 1 by y to the power n dy by dx is equal to 1 by 1 minus n dv by dx. Now we can substitute this term in this equation here and write down 1 by 1 minus n dv by dx plus this 1 by y to the power n minus 1 is taken as v here. So this becomes v into p of x is equal to qx, and we will multiply 1 minus n everywhere because this coefficient must be 1. This becomes dv by dx plus 1 minus n into p of x into v is equal to 1 minus n into q of x. This is the formalism, and we know the solution of this linear ordinary differential equation, that is v into integrating factor is equal to integral of q of x into integrating factor, and there is 1 minus n term also, and this integration is with respect to x plus an arbitrary constant c. This is the general formalism. I think you got the part here, and let me take an example by which you will be more clear. So the example is given something like this: x into dy by dx plus y is equal to x to the power 3 y to the power 6, and the initial condition is y at x is equal to 1 is equal to 1. Now our first job is to get rid of this x here, because we want the coefficient 1 first. After that we will do how these Bernoulli's equations are done. Then we divide x everywhere. We get this equation dy by dx plus y by x is equal to x square y to the power 6. Now we bring this y to the power 6 to LHS, and this becomes 1 by y to the power 6 dy by dx is equal to sorry, this is plus, and here 1 by x y to the power 5 is equal to x square. Now we can put 1 by y to the power 5 as v, and after differentiating this we will get dv by dx is equal to minus 5 by y to the power 6 dy by dx. Then we will get minus 1 by 5 dv by dx is equal to 1 by y to the power 6 dy by dx. And we can substitute this value in this equation here, and this becomes minus 1 by 5 dv by dx plus v by x is equal to x square. And again we have to multiply minus 5 here to make this coefficient 1, and this becomes dv by dx minus 5v by x is equal to x square. Now this is converted to a linear ordinary differential equation. We can find the integrating factor for that equation. This becomes minus e to the power minus 5 by x dx, and this becomes e to the power minus 5 log x, and we know the value of this. This is 1 by x to the power 5. Now put this integrating factor and find the solution. That becomes v into 1 by x to the power 5 is equal to xx square by x to the power 5 dx plus arbitrary constant c. So we will get v by x to the power 5 is equal to yeah, I have left minus 5 somewhere, I think. Yeah, here minus 5. So here there is some minus 5 term also. This become, yeah, so this becomes minus 5x cube dx plus c. Finally we will get v by x to the power 5 is equal to 5 by 2x square plus c. And after substituting the value of v, we will get 1 by x to the power 5 into y to the power 5 is equal to 5 by 2x square plus c. Now we have been given this condition that y at x is equal to 1 is 1. So this becomes 1 is equal to 5 by 2 plus c. Now by taking this term to this side, we will get c is equal to minus 3 by 2. And the final solution we get is 1 by x to the power 5 y to the power 5 is equal to 5 by 2x square minus 3 by 2. This is the answer. So what we did in this kind of ordinary differential equation is, first we have been given a differential equation in which in the right hand side y to the power n is multiplied, and we first take this y to the power n term to LHS and divide throughout this LHS, and then we consider this 1 by y to the power n minus 1 as v, and after differentiating we can substitute this term as the first term in the LHS. Then this will be reduced to a linear ordinary differential equation, and we know how to find the solution. So this is the main formalism, and we did an example also here. I think this part is clear. Now I am giving you another homework. So basically you have two homeworks and you can solve these two homeworks. So the question is like this: there is a radioactive substance and this disintegrates at a rate which is proportional to the amount of substance present, and it is given that 50% of this substance disintegrates in 1000 years. So find the amount of this substance that will disintegrate in 50 years. And here you can take e to the power x as 1 minus x. We have an hint here, and the options are 1.5%, B is 2.5%, C option is 3.5%, and D option is 4.5%. So I will advise you, this formula from nuclear physics already, radioactivity law, but I will advise you try to establish the differential equation first, then solve it and find the solution of the differential equation. After that you can proceed. Okay, so now I think I should stop here, and we will meet in the next lecture. So till then, stay home, stay safe, and bye bye. See you in the next lecture.